It is 1666, and England is in crisis. The dreaded plague is spreading north from London. The universities close, and both students and teachers head home to safety, and one such student heads north to his family's estate in Lincolnshire. One afternoon, while sitting drinking tea, he observes an apple fall to the ground and begins to speculate about why all objects are drawn to the Earth's centre. Eventually, nearly 2 decades later, the same man publishes his theory of universal gravitation, which, for the first time, lays down the laws of gravity and simultaneously revolutionizes mathematics, physics, and astronomy. His name? Sir Isaac Newton, history's greatest scientist. The man known to history as Isaac Newton was born on Christmas Day, the 25th of December, in the year 1642, at the manor house of Woolsthorpe, south of the town of Grantham, in Lincolnshire, in the East Midlands of England. The Julian calendar was still in use in England at the time, and it was the 4th of January 1643 on the continent, where most countries had adopted the Gregorian calendar that was 10 days ahead of the Julian calendar. Little Isaac was clearly sickly and underweight, and it is understood that his mother believed he would die shortly after being born, a development which explains why he was not baptized for a week after his birth, a ceremony which usually took place within 48 hours of the birth. Whatever the circumstances, Isaac pulled through and survived. He was named after his father. Isaac Newton Sr. was a landholder and an important farmer in rural Lincolnshire. The family's wealth was indicated by the fact that they lived at Woolsthorpe, a substantial enough manor house. The Newton family had built on generational upward social mobility here from the early 16th century onwards, and had become prominent members of the yeomanry by the middle of the 17th century, the equivalent of being middle-class farmers. Isaac Sr. was uneducated and illiterate, a not uncommon state of affairs for middle-class yeomen in the 17th century. Isaac would never know him. His father died in early October 1642, at 36 years of age, 2.5 months before his one and only son was born. He left behind a sizable enough estate and a range of livestock that included 4 dozen cattle and 235 sheep. This wealth would have a bearing on Isaac's life and allowed him to pursue a life of scholarship in later years. Isaac's mother was Hannah Newton, the daughter of James Askew, a member of the gentry from the town of Market Overton in Rutlandshire. It is a sign of Isaac Newton Sr.'s upwardly mobile nature and economic success that he had married Hannah, whose father was of a higher social status than the Newtons. She eventually remarried after her first husband's death. Her second marriage was to the Reverend Barnabas Smith, a churchman with a large estate that generated an income of around £500 per year, a substantial amount of money in the middle of the 17th century. When she married Smith, Isaac's mother left to live with him at North Witham, around 3 kilometres away from Woolsthorpe. There she started a new family. Isaac was not a part of it. When his mother headed to live with Smith, she left her firstborn son with her parents. Evidently, Isaac's childhood with them was not a pleasant one. Years later, when his grandfather died, it was revealed in his will that he had left Isaac nothing, suggesting a frosty relationship. In all of his extensive correspondence over the decades, which has all been analysed in detail by historians, there is no mention of his grandfather Askew, and his grandmother was not exactly spoken of glowingly by Isaac on the few occasions in which he mentioned her. Finally, it has also been speculated that Isaac grew to loathe his stepfather, the Reverend Smith, an understandable development if he felt abandoned by his mother and was left to grow up in a house where his relationship with his grandparents was strained. Historians have concluded that the peculiar elements of Isaac's later personality, his aloofness and distance from others, were shaped by these early childhood experiences. Newton's life was also influenced greatly by intellectual, cultural and social forces which had commenced well over a century before his birth. The Renaissance is typically viewed through an artistic prism as a movement that led to the emergence of great painters, sculptors and architects. In reality, it transformed every sphere of European life in the 15th and 16th centuries, from philosophy and diplomacy to commerce and technology. One of the offshoots of it was the scientific revolution. Medieval European science was primitive. A certain amount of knowledge about astronomy as well as biology, mathematics and the natural sciences had been retained from the ancient Greeks and Romans. Yet, in many spheres, European scientific knowledge was remedial in medieval times. That all began to change in the early 16th century. First, a Polish man, Nicolaus Copernicus, published a book entitled On the Revolutions of the Heavenly Spheres in 1543. In this, he laid out the heliocentric model of the universe, which stated that the Earth rotated around the Sun and that the Earth was not the centre of existence. Copernicus's work opened the floodgates for a wave of new scientific inquiry. Soon figures like Tycho Brahe in Denmark, Johannes Kepler in Germany, and Galileo Galilei in Italy were conducting groundbreaking work on astronomy, optics, mathematics and physics. They also began developing scientific instruments like telescopes and measuring tools. The scientific method emerged too. This was the idea that a person could come up with a hypothesis and then test that through experimentation and reasoning. This work was related to philosophical inquiry, which had long used such methods going back to the ancient Greeks. It was also in ancient Greece that philosophers began conceiving of the world as being made up of tiny particles which they had called atomos, the root of the modern word atom. In line with this, the scientists of the European scientific revolution viewed themselves as being natural philosophers. There was an English dimension to all of this, though the scientific revolution arrived at England later than most other parts of Western Europe. One of the earliest proponents of the new science was Sir Walter Raleigh, the famous Elizabethan courtier. Raleigh fell out of favour after Elizabeth's death and was imprisoned in the Tower of London for 13 years between 1603 and 1616 by the new king, James I. There he set up a laboratory and spent much of his time carrying out experiments. Elsewhere, the drive to discover the northeast and northwest passages to Asia by sailing north of Europe or America had led English navigators to develop scientific instruments and accomplished cartographic or map-making skills in the 16th century. But it was really in the 17th century that England came into its own as a centre of the scientific revolution. The Lord Chancellor of England between 1617 and 1621, Sir Francis Bacon, was known for his contributions to the scientific method and inductive reasoning. William Harvey, an English physician of the early 17th century, conducted groundbreaking work on the circulatory system and human anatomy. By the time Newton was born, Robert Boyle, the youngest son of the first Earl of Cork, Richard Boyle, was commencing his pioneering work in chemistry. He is now deemed to be the father of modern chemistry. There were many other natural philosophers beginning to make contributions here and there to the various fields of science. All of their activities gained greater coherence and collegiality in 1660, when the Royal Society was founded in London as a means for scientists to swap ideas and correspond about their research. Newton would soon emerge as the greatest figure of the scientific revolution in England. Not much is known about Isaac's earliest years. He was reluctant to write about his childhood and later life. His stepfather died in 1653 when Isaac was 10 years old. His mother then returned to Woolsthorpe along with Isaac's younger 3 half-siblings. By then, Isaac's education was already well underway, guided by a cousin, another churchman, named Richard Askew. In 1655, when he was 12 years old, he was sent on to a grammar school in the nearby town of Grantham, where he was taught by a Mr. Stokes. The curriculum would have had a heavy emphasis on learning Latin, and then that stemmed outwards into the subjects that were written about by the greatest Latin writers, namely Roman authors like Cicero, Quintilian, Virgil, Tacitus, Seneca, and the like. The subjects were rhetoric, history, prose poetry, and philosophy. Still, recent research has revealed that Mr. Stokes did have a good bit of mathematical knowledge too, and Newton's abilities in this area were consequently fostered from around age 12 or 13. Isaac, who would notably display almost no interest in the opposite sex as an adult, appears to have had a teenage romance with the stepdaughter of a Mr. Clark with whom he lodged at Grantham. In 1659, when he was 16 years old, he was recalled home to Woolsthorpe to help out on the family farm, but this was a short-lived experiment. Isaac hated farm work, and both Mr. Stokes and his cousin Richard Askew had learned enough about his intellect to realize that he had the makings of a gifted scholar. They organized to help finance the finishing of his elementary schooling, and then, with this done, he was sent off to Cambridge University in 1661. Newton's earliest years at Cambridge were formative in his emergence as one of the greatest scientific minds in human history, though often in unusual ways. His comparatively humble background meant that he was assigned as a sub-sizer. This meant he was expected to earn his keep cleaning the college and was not allowed to dine with the other wealthier students. This suggests his mother had refused to provide much financing from the estate she now controlled from not one, but 2 deceased husbands. What it did ensure was that Newton was somewhat socially isolated as a lowly sub-sizer, something which encouraged him to focus more on his studies. Early on, he was taught by Benjamin Pullin, a tutor who assigned him lots of writings by the giant of the medieval scholastic curriculum, the ancient Greek polymath Aristotle, a man who was primarily remembered as a philosopher, but who was also one of the great early natural scientists. Before long, Newton was moving on to more contemporary scientific works and had developed an especially keen interest in physics. About 2.5 years into his studies at Cambridge, he then abandoned any sense of formal or structured learning. His lengthy notebooks, which have survived down to the present day, show that he stopped reading the works of Aristotle and other canonical Greek and Roman works by figures like Plato. Instead, Newton began to concentrate overwhelmingly on more modern scientific, philosophical and political writings. Robert Boyle's pioneering chemistry work featured amongst what he was interested in, as was Thomas Hobbes' great work of political theory, Leviathan, published just a few years earlier in 1651. However, it was the works of Galileo that held Newton's attention above all others at this time. The Italian polymath had revolutionized the study of astronomy, optics, and many other fields in a series of studies carried out between the 1590s and 1630s. Decades later in England, they were inspiring Newton to break with the established curriculum at Cambridge and begin his own highly original research on mathematics, physics, and optics. Newton's education at Cambridge was coming to an end just as a series of events in England would create an ideal environment for him to carry out one of the most miraculous periods of research and writing ever undertaken in the history of science. Late in 1664, a large comet was seen over southern England. In the minds of early modern English people, this was a celestial portent of bad times ahead. Early in 1665, their worst fears were confirmed when a virulent wave of the bubonic plague struck England. While the plague's most terrible moment had come in the late 1340s and early 1350s, when it killed upwards of 1 out of every 3 Europeans, smaller waves of the disease struck the continent periodically for centuries to come. Crowded, dirty cities were particularly susceptible to plague pandemics, and these outbreaks even reached the streets of relatively small university towns like Cambridge. For instance, an outbreak of the disease in 1603 had killed an estimated 25,000 to 30,000 people in London, over 10% of the whole at the time. There was no cure or no effective way of fighting it other than to flee from urban areas and avoid contact with others who carried the disease. Thus, when the plague arrived, the wealthier people who were able to do so often fled from London, Bristol, Cambridge and Oxford to their country houses and spent months there. This is what happened in the plague year of 1665, a particularly destructive wave of the disease which killed upwards of 100,000 people in London in the mid-1660s, about 15% of the total population there at the time. Cambridge University closed, and Newton retreated to his family estate at Woolsthorpe. The isolation and lack of interruption would allow him to produce an enormous array of work, such that this period in 1665 and 1666 is often termed Newton's Annae Mirabilis, or miracle years, much like that which Albert Einstein had centuries later in 1905, when he published 4 papers within the space of a few months, which revolutionized the study of physics. Newton's work in his miracle years can broadly be broken down into three key fields: physics, mathematics, and optics. Despite the tendency to view this as a period of miraculous discovery, Newton was building on work he had been carrying out during his years at Cambridge, and which he had kept extensive notes of in a book which he inscribed with the title Quaestiones Quaedam Philosophicae, meaning certain philosophical questions, though the topics covered were concerned with the hard sciences. His first major discoveries were mathematical. They resulted in the development of the binomial theorem in 1665, a mathematical concept which allows for expansion of much more basic theorems like x plus y. This was the foundation for further work which involved measuring large objects and their movement, as well as algorithms for tracing curves, tangents, and the like. No other mathematician in Europe had ever arrived at findings that were this complex before. They laid a lot of the basis for the development of modern calculus. Newton's response to making these discoveries was to record them in a paper which he entitled, "To resolve problems by motion, these following propositions are sufficient." He then placed the paper in a drawer and forgot about mathematics for at least 6 months. He would not make any effort to publish or disseminate that work at the time. With this done, and still mired in his continuing self-imposed exile from the plague, Newton moved on to studying mechanics. His mathematical inquiries were related to this, as basic study of weights, measures, and mechanics requires use of mathematical equations. Newton wanted to build on the work of Galileo and René Descartes in this area, the latter a philosopher who 30 years earlier had come up with the famous phrase cogito ergo sum, I think, therefore I am, as a basis for an objective, unquestionable truth that could form the foundation of a philosophical system. Building on their work and using his own complex mathematical abilities, Newton now began to work out a new theory of how gravity functions. By studying how objects collided, he worked out that objects of any kind exert force over one another when they clash or meet. This sends them in different directions, but there is evidence of a center of gravity along a straight line. Experimenting further, he came to the conclusion that particles or atoms attract one another, and that the force involved in this gravitational pull correlates with the mass of the objects in question and the distance between them. It is a complex concept and was tied into several other conclusions he reached in his notebooks in 1665 and 1666 about how force, gravity, and mechanics operated. The simplest of these laws of physics which he devised at the time is the third law he wrote about. This states simply that every action has an equal and opposite reaction. When you jump into the air, this action is immediately followed by gravity pulling you back downwards to the ground by the same distance. While some of the laws concerning mathematics and gravity which he devised at this time were consequently more complex than others, what they amounted to in their entirety was a fundamental expansion on human understanding of how gravity and motion work. A fanciful story later developed that Newton had reached his conclusions about gravity after seeing an apple fall from a tree at Woolsthorpe. The tale was probably supposed to mimic a story about the ancient Greek mathematician Archimedes making one of his great discoveries while taking a bath and discovering the principles of buoyancy and displacement in the process. In the long run, Newton's discoveries around gravity, weights and mechanics in the mid-1660s were the most important. There was a third field, though, beyond mathematics and hard physics. Newton also made some important discoveries in the field of optics at this time, the study of light, colours and the visual world. From this, we can get a sense of how Newton carried out his research and experiments. He wanted to see if the rays emitted by different colours could be perceived in different ways. To achieve this, he first painted one end of a piece of thread red and the other blue, and then observed them through a prism. They looked disjoined, as he had expected, demonstrating what's known as the heterogeneity of light, the fact that light can appear more intense and available depending on different sets of circumstances. He then expanded the research by setting up a dark room, through which he only allowed in a narrow beam of light. Then he placed a prism in front of the beam and refracted that onto a wall that was over 20 feet away. The resulting colour spectrum was 5 times longer than it was wide. What Newton consequently realised was that light was not homogeneous, but heterogeneous. It is not made up of one single thing, but is instead comprised of different parts which can be seen in terms of the different colours in a light prism. This is the corpuscular theory of light, as Newton would describe these parts which make up light as corpuscles. This research would become the foundational basis for Albert Einstein's subsequent discovery of photons nearly 2.5 centuries later. By the time 1666 came to an end, Newton had made a series of breakthroughs in the fields of mathematics, physics and optics. Nobody as yet, though, knew what he had accomplished. His remarkable findings were carefully recorded in his notebooks at Woolsthorpe, but he had not yet shared them with the world. It was the spring of 1667 before it was considered safe to return to Cambridge, as life in southern England was so disturbed by the final stages of the plague year and the Great Fire of London that had destroyed the capital in September 1666, leaving around 100,000 homeless, people who either encamped outside the ruins of the city or dispersed to other towns and villages around the country. In this atmosphere of disordered life, Newton arrived back at Cambridge and managed to gain election as a Fellow, a post that provided him with a modest salary. He began teaching, tutoring and continuing his research back at Cambridge. He also started to disseminate some of his findings in a limited way. For instance, he distilled some of his mathematical work into a tract entitled On Analysis by Infinite Series, which he then gave copies of to a number of colleagues. This was hardly the greatest example of academic self-promotion ever attempted, and it's debatable whether people he gave his findings to would have been able to follow the equations he laid out in all instances. It was nevertheless enough for it to be made clear to people at the university that Newton was a mathematician of unusual skill and that he had made breakthroughs during the plague year. He was, therefore, made the Lucasian Professor of Mathematics in 1669, a chair which had only been founded in 1663 through a bequest made by Henry Lucas shortly before his death. Lucas was a parliamentarian who had represented Cambridge during the English Civil Wars of the 1640s. Newton would hold the Lucasian Professorship for 33 years, though his final years were absentee as he moved to London in the mid-1690s. The position was hardly onerous. Newton was expected to deliver one lecture every week during one term of the year. For this, he was paid an income of £100 per year. Moreover, the lectures barely had any audience. Such was the lack of interest in mathematics and physics at Cambridge in the late 17th century. Even this light load was dispensed with by 1687, after which time Newton had no teaching responsibilities. What these lectures did do was allow Newton space to refine his findings from the mid-1660s and make them more accessible to an audience. To demonstrate his findings to the few students who attended his lectures, he began developing instruments to showcase his findings, notably a telescope and prism rings that showed his theories on optics. Very slowly his findings began to reach a wider audience. By 1671, the Royal Society in London had heard about his discoveries and invited Newton to send them information about his work. He was duly elected as a Fellow of the Society in January 1672. In the years that followed, his entry into the Royal Society would mean that his research findings began to spread beyond Cambridge to the wider academic community in England and then to the continent, as many members of the Royal Society corresponded extensively with natural philosophers and scholars on the continent. In an age before academic peer review journals, this was how new research was disseminated. As this happened, Newton refrained from publishing much of his work. His paper on analysis by infinite series was distributed and was eventually published in print in 1711, while another couple of works appeared as well, but Newton would ultimately wait over 20 years between when he made his breakthroughs at Woolsthorpe and when he published them in complete form. As Newton emerged in the 1660s and 1670s as one of the leading scholars of his day, he seemed to have no concurrent interest in starting a family or marrying. It was taken for granted in the 17th century that a man of his social status would marry, have children, and try to move up the social ladder. He would never do this and does not appear to have ever contemplated doing so. In fact, he seemed to have no interest in the opposite sex. This has understandably led to people questioning his sexuality. There is no evidence to suggest that Newton was gay. Instead, he just appears to have been largely asexual, with no interest of any kind in a sexual relationship. Historians were surprised to learn years ago about his possible fling as a teenager with the stepdaughter of Mr. Clarke, with whom he lodged in Grantham when he was attending the grammar school there in the mid-1650s, simply because it was so unusual. The conclusion we can draw from this is that he was heterosexual, but with very little interest in women. Over time, he abandoned any thoughts of marriage and a family, if he ever gave it much consideration at all. Instead, he committed himself fully to his research and writing. This included friendships. Newton was a reclusive individual who didn't socialize much at Cambridge. When he visited London in August 1674, he made no effort to meet any of the people at the Royal Society he had been in contact with for several years by then. Instead, he went back to Cambridge a week later and continued writing to them about his work. As he aged, he did become slightly more sociable. His religious views were also unorthodox. Newton was a Protestant, as were the majority of English people by the second half of the 17th century. He was a nonconformist, though, someone who disagreed with the established views of the Anglican Church of England. In Newton's case, his nonconformity was on the extreme end of the spectrum. He did not believe in the sanctity of the Trinity of God, Jesus, and the Holy Spirit. However, he kept his religious views largely to himself. It has only been possible to reconstruct them through analysis of his notebooks. Newton's aloof and often difficult personality could translate into rivalries and conflicts with fellow scientists as the years went by. There were occasions when this was the simple over and back between scholars with competing theories. This was the case with Newton and Christiaan Huygens. Huygens was a leading Dutch mathematician, natural philosopher, and astronomer whose work also focused on optics. For instance, while Newton was still a child, Huygens had discovered Titan, the largest of Saturn's moons, in 1655. He was a scholar of considerable renown around Europe when Newton was unheard of. Both men developed competing theories about the nature of light. Huygens disagreed with Newton's corpuscular theory of light and instead proposed that light travelled as waves that then produced secondary waves or wavelets. A considerable academic debate played out between Newton and Huygens over many years about this. More toxic was the rivalry that developed between Newton and Robert Hooke. Hooke was 7 years older and was also a natural philosopher, mathematician, and astronomer. He dabbled in surveying and engineering too, and had overseen a lot of the work which went into rebuilding London after the Great Fire of 1666. Hooke was working on telescopes, optics, and gravity in the 1660s and 1670s, and viewed Newton's emergence as a threat to his eminence within England's scholarly community. An unpleasant rivalry developed, one which lasted decades and which famously is believed to have ended with Newton having all portraits of Hooke held by the Royal Society destroyed after his rival's death in 1703. Rivalries aside, Newton had something in common with many of these other English natural philosophers. They were all generally interested in alchemy, esoteric thought, and what was known in early modern Europe as Hermeticism. Newton's interest in these pursuits was lifelong. Alchemy is a field in which individuals sought to discover the fabled philosopher's stone, a legendary substance which alchemists believed could turn anything into gold. It was closely allied to a belief in magic and elements of esoteric or hidden history and arcane knowledge. Hermeticism was a branch of alchemical studies. The word comes from a set of teaching which were believed to have been written by a mysterious figure from late antiquity known as Hermes Trismegistus. He was understood to have been a philosopher and a proto-scientist who dabbled in alchemy. In reality, the works which early modern Europeans ascribed to him were largely derived from a mix of Neoplatonic philosophy by 3rd century AD writers like Plotinus and science as it had been carried out in the Roman Empire in the 3rd and 4th centuries AD, while elements of ancient Egyptian law and other writings were also incorporated into Hermetic and alchemical thought in early modern Europe. As such, Hermeticism was a kind of pseudo-religion and experimentation with arcane knowledge. It was very closely connected to the scientific revolution, and Newton and Leibniz were far from the only major scientists of the era who dabbled in alchemy and Hermeticism. So too did figures like Nicolaus Copernicus, Tycho Brahe, Johannes Kepler, Galileo, Walter Raleigh, Francis Bacon, Robert Boyle, and many others. The scientific revolution was deeply connected to the quest for the philosopher's stone, alchemical studies more broadly, and Hermetic thought. Chemistry, in particular, emerged as a discipline directly from alchemical studies. Thus, a visitor to Newton's study over many years would have seen scientific instruments that were designed to test the suitability of substances as the philosopher's stone, while his papers are peppered with manuscripts about alchemy and Hermeticism. As early as the 1660s, Newton's interest in the burgeoning field of chemistry was leading to him conducting research in the field of alchemy as well. He had obtained a 6-volume work entitled Theatrum Chemicum, which was published back in 1602 and which contained extensive treatises on how to carry out alchemical experiments. Newton closely read this and other works on the subject, even as he was carrying out his groundbreaking work on physics and mathematics. By 1670, his alchemical studies were advanced enough that he composed a treatise of his own entitled The Vegetation of Metals. Vegetation meaning transformation in this case. By that time, he was considering moving away entirely from natural philosophy or physics to focus on alchemy. He entered into correspondence with the leading chemist of the age, Robert Boyle, and continued to develop his laboratory at Cambridge, carrying out new experiments and acquiring all sorts of substances and equipment with which to study them. This led to the creation of an Index Chemicus, or chemical index, in which he noted his experiments with hundreds of different substances to find the philosopher's stone. Newton would eventually develop files over thousands of pages of notes as part of his studies in alchemy. Unfortunately, much of this was in the form of symbols, which he clearly was able to understand himself, yet which are now impenetrable to the modern reader. It does add to the sense that he was engaged in arcane research, though. In fact, he probably gave over more of his time to this than the study of physics. This interest of Newton's in alchemy and Hermeticism extended into what we would call esoteric history and thought today. Esoteric means mysterious or hidden. An example of Newton's interests in this area was the myth of Atlantis that had been described at length by Plato in 2 of his dialogues, the Timaeus and the Critias. Newton incorporated discussion of the fabled utopia into a long book, which he wrote entitled The Chronology of Ancient Kingdoms Amended. This explored the chronology of ancient societies, like those of ancient Egypt and Greece, the Babylonians, the Assyrians and the Persians and so forth from antiquity. It must be remembered that when Newton was writing about these, the modern disciplines of Egyptology, Orientalism and archaeology had yet to emerge, and the history of ancient Egypt and Mesopotamia was still shrouded in mystery. Some of his work was historically based. Other parts of it involved an eclectic blend of history and myth. It fed into his interest as well in the Old Testament and more obscure elements of Christian theology. For instance, Newton was fascinated by the Book of Daniel, an apocalyptic text of the Old Testament in which the end of days was discussed. Worryingly, this research into apocalyptic texts would eventually lead Newton to calculate that the world could end in either 2034 or 2060. We might not have long left. This interest in the more obscure historicity of the Old Testament saw Newton also writing in his extensive notes about the Temple of Solomon, the first Temple of Jerusalem in the Holy City, and whether it had in fact been built by King Solomon. Newton concluded that these ancient buildings and the religions around them were evidence of long-lost knowledge systems of the ancients, which alchemical studies formed just one prong of efforts to recover. In the end, Newton did not decide to abandon his work as a natural philosopher to become an alchemist, a transition which, to put it in modern terms, would have seen him switching from studying physics to chemistry. Instead, he continued to focus on natural philosophy, moonlighting in alchemy. We are fortunate that he did, for in the 1680s he began working on condensing his research and findings into one of the most important books ever written in the history of science. This was entitled the Philosophiae Naturalis Principia Mathematica, meaning the mathematical principles of natural philosophy. Finished in 1686 and then published in 1687, it contains a synthesis of all the work which Newton had undertaken since his student days at Cambridge. While he had disseminated quite a lot of this since the mid-1660s in the form of papers and through extensive correspondence, this was a much more refined account of his findings in the sphere of gravitational laws, mechanics, and mathematics. It added greatly to European scientific knowledge. For instance, while Galileo and Kepler had observed and described planetary motions nearly a century earlier, Newton was now able to provide a scientific and mathematical explanation for why the planets moved in the way they did. It also added to knowledge about the equinoxes and the world's ocean tides. Newton even theorized about how the theory of gravity, which he had proposed over 20 years earlier, could account for physical phenomena like observations of irregular motions in the moon. It would soon come to be regarded as the most important book written during the scientific revolution. The Principia Mathematica was broken down into 3 books. The first book, entitled De Motu Corporum, or On the Motion of Bodies, provided a detailed description of his theories around gravity and the laws of motion, as well as exploring the ideas of gravitational pull, force, and equal reactions that he had discovered at Woolsthorpe all the way back in 1666. This included additional discussion of the work of earlier scientists like Johannes Kepler and how bodies moved owing to things like centripetal force. These theories were then expanded upon in Book 2. Here, he was responding directly to arguments that had been made by René Descartes and others on the continent in decades gone by, and systematically showing where they had gone wrong in their analyses. Finally, in Book 3, subtitled as De Mundi Systemate, or On the System of the World, Newton attempted to demonstrate what the real-world implications of the theories he had described in the first 2 books were. For instance, there was a lot of discussion in Book 3 of how the laws of gravity and force, which he had detailed in Book 1 and Book 2, impacted on the planets and the solar system. In the course of this, Newton also laid out his own views on the nature of the solar system and the heliocentric universe. In this way, the Principia Mathematica was not just laying out new theories. It was discussing the vast range of material which constituted the scientific revolution, going all the way back to Copernicus's discoveries about the solar system and the Earth revolving around the Sun a century and a half earlier. If there is one thing that takes a small shine off Newton's accomplishments, is that many of the same conclusions were arrived at completely independently at the exact same time, hundreds of kilometers away in Germany. Gottfried Wilhelm Leibniz was born in 1646 in the city of Leipzig in Saxony in eastern Germany, a few years after Newton's birth in England. He attended numerous universities in the 1660s and then embarked on a career of exceptional scholarship. Like Newton, Leibniz was a polymath who cannot be easily categorized as a mathematician, a physicist, or a philosopher. He worked in an extensive range of fields and, as Newton increasingly would as his life went on, he also worked for the government and performed a range of administrative and bureaucratic roles, even working for Peter the Great, Tsar of Russia, to modernize the Russian state in the early 18th century. Leibniz's research led him to make many of the same discoveries that Newton was making in England between the 1660s and 1690s. In particular, both men made the same breakthroughs in developing the field of calculus, though Leibniz was more practical in his application and even invented the Leibniz wheel as a kind of basic mechanical calculator. So similar were the discoveries that the two men made completely independent of one another that later in their lives an academic argument broke out in which they both claimed to have been the first to make their discoveries. In the course of this, Newton disingenuously used some letters he had written to and from Leibniz back in the 1670s to try and claim his German counterpart had copied his findings. If nothing else, what this demonstrates is that societies have to arrive at a certain threshold of knowledge in a given discipline before individuals can make specific breakthroughs. Both men reached the same conclusions at the same time because they were building on the work of Galileo, Kepler, and others. Similar phenomena are seen in other time periods. Over a century and a half later, both Charles Darwin and Alfred Russel Wallace would arrive at almost identical ideas about evolution and the survival of species independent of one another, yet at the same time. Newton published the Principia Mathematica just as England was entering into a period of pronounced political instability. 2 years earlier, in 1685, King Charles II had died. Although he had fathered a huge number of illegitimate children with over half a dozen different mistresses, his marriage to his Portuguese wife, Queen Catherine of Braganza, had been childless. Without a direct, legitimate heir, the throne passed to his brother, James, Duke of York. The problem was that the newly ascended King James II was a Roman Catholic at a time when anti-Catholic sentiments in England and Scotland were running very high. An already unstable political dynamic boiled over when a son was born to James in the summer of 1688, one who would now be raised as a Roman Catholic, putting in place the possibility of an extended return back to Catholicism in England. James did nothing to alleviate these concerns and unwisely began placing Catholics in positions of power in England and Ireland. Within weeks, a powerful alliance of English aristocrats and politicians had written to James's son-in-law, William of Orange, the most powerful figure of the Dutch Republic and the husband of James's daughter, Mary. They offered him the throne, and William duly headed to England with an army to enforce his claim. By the time the year 1688 was out, James had fled to France, and William and Mary were about to become joint rulers as King William III and Queen Mary II. The Glorious Revolution was a period of instability, and it continued into the 1690s as war followed between England and the Dutch Republic against the French, who were backing James's claim to be restored to his throne. These events had a bearing on Newton's career. His aloof character meant that he had always avoided becoming involved in Cambridge's politics. However, early in 1687, while he was still king, James II had attempted to take over the university politically by installing Roman Catholics like the Benedictine monk Alban Francis as members of the Senate that ran the institution. This annoyed Newton, a religious nonconformist who viewed even Protestant Anglicans poorly and who perceived Catholics as adherents of a branch of Christianity which had little or no basis in Scripture. He therefore became involved in the internal wrangling at Cambridge to try to maintain the political and religious independence of the university. In 1688, this led to Isaac and 7 others being ordered to come to London to answer for their efforts to resist James's attempts to enforce control over Cambridge. This brief foray into political activity was enough that when the Glorious Revolution had occurred, and a new Convention Parliament was being assembled early in 1689 to ratify the political changes, Newton stood for election at Cambridge. He won a seat and headed for Westminster. His contributions were limited. Newton backed the constitutional changes which saw William and Mary become king and queen on the basis that Parliament's power relative to the monarchy was vastly increased in England, but he never spoke before the Parliament. A legend has it that the only vocal contribution he made to the Convention Parliament was to ask an usher to close a window that was creating a draft. Despite this, he was elected again as a member of Cambridge University in 1701, though a third election attempt in 1705 was unsuccessful. More broadly, Newton's brief forays into politics were important in that he spent more time in London and his social circle expanded slightly. In particular, he developed a friendship with the noted philosopher John Locke, whose areas of focus were optics and epistemology, the theory or study of knowledge. Life in London saw him become a government employee. In 1695, he was one of 8 individuals that the government contacted about the issue of English coinage being clipped. By the late 17th century, money was still circulating exclusively as coins made out of metals like silver and copper. Notes were starting to appear as instruments of exchange within the business community, but it was a long time before they would become part of day-to-day economic life. The issue with the coinage in the 1690s was that the stresses of war with France following the Glorious Revolution had led to people clipping the nation's coins. This is where a small sliver of silver was clipped or cut off the edges of coins. If this was done with a large amount of coins, a person could get themselves a nice haul of silver. Clipping was reaching epidemic proportions by the mid-1690s, and Newton was one of the individuals contacted about coming up with a solution. This first engagement with the government led to him being offered the post of Master of the Mint a year later in 1696. Over the next 2.5 years, he oversaw a complete recoinage. This was where an early modern government called in all of the old coins, melted them down, and minted new ones that were reissued. The new coins were issued with features which made it obvious if they had been clipped. Nearly £7 million worth of coins were minted and issued between the spring of 1696, when he became Master of the Mint, and the end of 1698, roughly the same amount as was usually issued over 30 years. The accomplishment points towards Newton's considerable abilities as an administrator, though his coins were undervalued by comparison with European silver, and England's new silver coins soon started vanishing to France, where people could exchange them for higher amounts of money. Despite his position as the leading natural philosopher of his age in England, Newton had only played a limited role in the activities of the Royal Society for much of his life. This was broadly owing to his acrimonious relationship with Robert Hooke. Hooke had a lot of supporters within the Society, and Newton had been marginalised within it as a result. However, Hooke died on the 3rd of March 1703, paving the way for Newton's rapid ascent. Many members of the organisation felt it was in need of a more scientific-minded leader after years in which two nobles, Charles Montague, 1st Earl of Halifax, and John Somers, 1st Baron Somers, had held the position of president. In this vein, at a meeting of the Society's members in November 1703, Newton was elected as the new president. He would hold the position down to his death, becoming the second longest-serving president ever, eclipsed only by Sir Joseph Banks, who held the office for a huge period of over 41 years between 1778 and 1820. 2 years after he became president of the Royal Society, Newton was also knighted, becoming the first scientist or natural philosopher ever to be awarded such a title in Europe. As president of the Royal Society, one of Newton's foremost achievements was balancing the Society's books. It was badly in debt in 1703. By 1710, he had not only managed to remedy its financial situation, but had also enough of a surplus to acquire a new property at Crane Court, near Fleet Street in London, which became the Royal Society's home in London for many years. Other actions were less admirable. He developed a rivalry with John Flamsteed, the head of the Royal Greenwich Observatory, resulting in Newton trying to suppress Flamsteed's work and steal his research. The whole episode highlights the more unsavoury elements of Newton's personality. While Newton's dual roles as Master of the Mint and President of the Royal Society kept him busy with government duties of one kind or another from the mid-1690s onwards, he did find time to continue his scholarly research and publishing. In 1704, he published Opticks, or a treatise on the reflections, refractions, inflections, and colours of light. In this, he expanded on his earlier work in the nature of light and how humans observed light refraction through glass and other substances. This was a synthesis of things Newton had written and lectured about since the 1660s. For instance, it contained one of the first detailed discussions of how light, when filtered through a glass prism, separates into different colours, the same thing which is witnessed in rainbows. This involved a fundamental revision of Western ideas about the nature of light. Going all the way back to studies conducted by Aristotle in ancient Greece, it had been assumed that light was one single colour. Newton made it clear that this was not the case. The book also expanded on the idea of historical method and research. His decision to publish the first edition of the book in English, rather than in Latin, was also important, signalling a shift away from the medieval and Renaissance notion that Latin was the unquestioned language of scholarship. Newton also spent a lot of time working on an expanded and revised second edition of the Principia Mathematica, published in 1713. As his efforts to suppress John Flamsteed's work and plagiarize his research indicates, Newton was also quite interested in astronomy and study of the stars in his later years. In this, he collaborated with Edmund Halley, the English astronomer who Halley's comet is named after. Halley used Newton's gravitational laws to calculate how often the comet would be visible from Earth, coming to the conclusion that it would be seen approximately every 75 years. Newton turned 70 years old at the very end of 1712. This was quite old by the standards of the 18th century, and his thoughts were now turning to his legacy rather than any sort of groundbreaking new work. Over the next decade and more, he published several new editions of his works, notably a French edition of Opticks, which made his research and findings more widely available on the continent. He entered into numerous arguments with other scholars on the continent about who had developed particular theories first. Newton was also employed by the government on a number of different scientific projects. One involved efforts to find a way of measuring longitude while at sea. The British Royal Navy had emerged as the finest navy in the world, and as Britain's colonial and imperial expansion accelerated, the government wanted to find better and better ways to explore the uncharted parts of the world. Newton spent time in his later years reading papers that discussed various theoretical ways of measuring longitude, but a fully functioning marine chronometer would not be successfully developed until John Harrison in 1761. Beyond this, Newton spent a lot of his later life returning to the study of esoteric subjects and theology which had held his interest throughout his life. His research on prophecies and apocalyptic religious thought were eventually published after his death as Observations upon the Prophecies of Daniel in 1733. In this, he had pondered the possible end of the world as his own life was also winding down. His health deteriorated from 1722 as he entered his 80s, though he continued to work. On the 2nd of March 1727, at 84 years of age, he chaired a meeting of the Royal Society. Afterwards, he became ill and his health deteriorated quickly. Newton died on the 20th of March 1727, the 31st of March on the continent. He was laid to rest in Westminster Abbey after a funeral attended by the leading figures of his age. Newton had been remarkably reticent about publishing his research during his lifetime. More than 20 years elapsed between his period of great discovery in 1665 and 1666 and when he finally published his work fully in the Principia Mathematica in 1687. This was mirrored in the amount of work which was left unpublished at the time of his death. Therefore, nearly more of his research was published posthumously than had been so during his lifetime. In 1728, just a year after he died, a collection of his lectures and writings on optics from Cambridge was published. That same year, his Chronology of Ancient Kingdoms amended, his work of history and theology that he had worked on over many years, appeared in print. 5 years later, his apocalyptic text of Observations on Daniel and the Apocalypse of St. John was also published. In 1754, the text of his correspondence with John Locke on scriptural matters was published as An Historical Account of Two Notable Corruptions of Scripture. As such, A lot of Newton's esoteric and theological work was published not long after he died. In many ways, though, the most consequential of all of Newton's written output are his extensive notebooks, correspondence and working papers, huge amounts of which have survived. His notebooks are generally found in the libraries of Cambridge University, though one of his earliest notebooks, dating all the way back to 1659, is today housed in the Morgan Library in New York. Extensive correspondence is extant by him, generally at Cambridge for the period of his life, prior to moving to London in the mid-1690s, and then in the National Archives of the UK in London for the years after he moved to the capital. With extensive digitisation and transcription, Newton's entire research career and virtually everything he wrote is available for the whole world to consult online today. Newton was already regarded as one of the geniuses of European scholarship and science in his own lifetime. His reputation in the 18th and 19th centuries was similar to that of Albert Einstein in the modern world. And yet, just like Einstein, Newton's work has been re-evaluated over time and revised. For instance, his work on gravity did not take account of how gravitational pull occurs beyond Earth itself and how it is impacted by things like black holes. There was simply no way for him to even begin measuring this in the 17th century. In this sense, it could be said that Newton's law of gravity was incorrect, but this misses the point. It was a stepping stone towards a more perfect understanding of how gravity functions. Science is a journey rather than a destination. The same thing has happened with Einstein's theory of general relativity. While it might have transformed the field of physics at the start of the 20th century, it is now appreciated that there are several theoretical shortcomings within it. But, like Newton before him, Einstein didn't have the benefit of the kind of technology available to modern physicists like quantum computing and the Large Hadron Collider at CERN in Switzerland. The re-evaluation of the transformative work of figures like Newton and Einstein is a normal process in the evolution of knowledge. Each generation builds on the last and eventually reaches a new threshold of knowledge based on earlier findings and new ones. There is no denying Newton's influence, though, on all those who came after him. The great theoretical physicist, Stephen Hawking, called the Principia Mathematica the most important book ever written on the hard sciences. Many would still agree 3 centuries after Newton's own time. Isaac Newton was undoubtedly one of the greatest figures of the scientific revolution. The peculiar thing about this is that his background would not have suggested his emergence as a great scientist or natural philosopher, as it was known in the parlance of the time. Newton hailed from rural England and came from a difficult family background, complicated by the death of his father before he was even born. There was no tradition of scholarship in his family. Indeed, his father and several other family members were illiterate. This being said, his family background possibly drove him to intellectual pursuits. Ensconced in a dynamic where he was marginalized by his mother's second marriage, he applied himself to his studies. A number of early influences, like his teacher at the grammar school in Grantham when he was young, Mr. Stokes, imparted the basics of mathematical inquiry to Newton. Then he went to Cambridge. He never applied himself in a dedicated manner to the standard curriculum. Instead, Newton began his own investigations into physics, mathematics, and optics based on his reading of thinkers like Galileo and Kepler, whose works were still revolutionary in the 17th century. Based on these and his own penetrating mind, he developed some of the most important concepts about how gravity functioned, as well as calculus and optics, all while he was still in his early 20s. 2 decades later, in 1687, he published one of the most important books ever written in the history of science, the Principia Mathematica. His story also points towards the unusual nature of the scientific revolution and the way that science and government overlapped to a greater extent in the 17th and 18th centuries than they do today. Newton, for instance, pursued studies in alchemy and esoteric knowledge, like all of his contemporaries in the field of natural philosophy. Later in life, he was drawn into government service and became Master of the Royal Mint in England. Throughout his life, he remained a difficult individual who few people knew much about on any personal level. In short, he was both complicated and brilliant. What do you think of Isaac Newton? Was he one of the most radical thinkers in the history of Western thought, or does the fact that Leibniz made many of the same discoveries as he did, independently of him, detract somewhat from the significance of Newton's work? Please let us know in the comments section. And in the meantime, thank you very much for watching.